Hello everyone and welcome back to this next lecture in the machine simulation series, and this is where we had left off last week, where we were talking about the vector cross product and how this vector cross product, which is basically defined between two vectors such as A and B, which are at an angle theta with each other, such that the result, which is the vector cross product, will always be in a plane which is perpendicular to the vector to the plane formed by these two vectors, right? And therefore, because of this kind of definition, it is extremely applicable to the case where we are finding out the force due to the magnetic field acting on a current carrying conductor. So in this lecture, I'm going to talk about how that's going to be done. So as always, before I start the lecture, a little bit of brief background, that if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length online courses that you can access on my website, which is pythonpowerelectronics.com. So on this website, if you go, this is the home page of the website. If you go to the button Learn, it will take you to the list of courses which I have currently. So currently I have 5 courses, and I'll go through them right away. So the first course I have is called Simulating Power Electronic Circuits Using Python. And in this I talk about how you can use Python and Python Power Electronics to simulate basic power electronic circuits. The second course I have is called Basics of Digital Signal Processing for Power Engineers, and in this I talk about how you can use Python and packages such as the SciPy package and the signal package within SciPy to analyze and design filters for power engineering applications. The third course I have is called Simulation of Magnetics for Power Electronics Using Python, and in this I talk about how you can use Python and Python Power Electronics to simulate magnetic components such as inductors, coupled inductors, and transformers. And the fourth course I have is called Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and packages such as the Python control package to design and analyze controllers for power electronic applications using the example of a single phase inverter connected to a single phase grid. And the very last course I have is a free course called Why Specialize in Power Electronics, and this course is targeted towards either junior undergraduate students or even high school students who are yet to choose their domain of specialization. And the purpose of this course is to tell them about the challenges and opportunities available in power electronics so that they may choose power electronics as their specialization. So all these courses are available on 2 platforms, which is Decibels Labs and Udemy. And if you click on any of these buttons, it will take you to the link for the course. So this page, the link for this page is provided in the description of this video. If you're interested, please do check it out. So with this, let me get back to the lecture. So as we were talking, just let me get back to the diagram. And in this diagram, or rather, let me go to the other diagram. So this is the diagram of the actual induction motor, rather a simplified diagram where we represent the entire stator winding as just a pair of slots which are diametrically opposite each other, and we represent the entire rotor as just these 2 concentric bars which are diametrically opposite each other. In reality, of course, the stator windings will be spread out throughout the circumference, and so will the rotor bars. The rotor bars are all over the rotor circumference. Now, we have already seen that because of the magnetic field produced by the stator and that interacts with the rotor, a current is produced in the rotor because an EMF is induced in the rotor. And since there is a current flowing on the rotor bars, because this current interacts with the magnetic field produced by the stator, a magnetic force is produced. And the same can be said for the lower rotor bar itself. There is a magnetic force produced here as well. And we have also seen, by using Fleming's left-hand rule, that the direction of the magnetic force is in the direction of this arrow for this upper rotor slot, rotor bar, and for the lower rotor bar, it is in this direction as shown in this arrow. And therefore it is very clear, because of these directions of these magnetic forces, a torque will be produced which will cause this rotor to rotate in the counterclockwise direction. Right? So this has all been discussed in the several lectures previous to this. Now, what I would like to talk about is I would like to write the equation for the magnetic force which is produced. So for that, we can go over to the other diagram. And here we have taken a very simplified case of a magnetic field which is acting on a current carrying conductor. So this rectangle, or rather this thin wire, is a current carrying conductor, and this arrow represents the direction of the current flowing in the current carrying conductor. Now we've already seen, because of this, a magnetic field is produced, and this magnetic field is produced in a plane which is perpendicular to this current carrying conductor. Now this magnetic field which is produced by the current carrying conductor will interact with this external magnetic field and will result in a force which is produced on the conductor, right? And we've also seen that we can use Fleming's left hand rule, where if you use, let me go over to the web browser and let me show Fleming's left hand rule. If you use your left hand such that the forefinger is pointing in the direction of the magnetic field, the middle finger is pointing in the direction of the current, then in that case the thumb will indicate the direction of the mechanical force which is produced. So if we go over back to our diagram, and if we use Fleming's left hand rule, you will see that if I point the forefinger in the direction of the magnetic field and the middle finger in the direction of the current, the thumb, which is the direction of the mechanical force, is coming out of the page. So this mechanical force will cause the conductor to jump out of the screen, right? Now, besides this, we had also seen that if the magnetic field were not exactly perpendicular to the current carrying conductor, but rather were at an angle such that this angle theta, let's say this is some angle theta, in that case, this magnetic field can be decomposed into two parts. That is, one part which is perpendicular to the current carrying conductor and another part which is in parallel to the current carrying conductor. Now, the component which is in parallel to the current carrying conductor will have no effect at all, whereas the component which is perpendicular to the current carrying conductor will, however, have an effect. Therefore, you can say that if this magnetic field were at an angle, then we can take the orthogonal projection of the magnetic field with respect to the current carrying conductor to calculate the magnetic force. So if we come over back to the browser and check out what the cross product is, if we were to say that the magnetic field were to be represented by this vector A and the current were to be represented by this vector B with an angle theta between them, then in that case the cross product will be the mechanical force and will be represented by AB sine theta. So now let's go back to our Excel sheet and let's write this down, because we are trying to calculate the electrical torque. So let us say that this mechanical force, right, is denoted by F, and there is a magnetic field whose strength is written by B. So this is the flux density, right? The flux density is merely the lines of force per unit area, right? And let's say I was the current flowing through the current carrying conductor. Then in that case, according to cross product, this would be equal to, the force would be equal to Bi sine theta. Alright. Basically all I'm doing is applying the cross product AB sine theta. Now, however, there is one problem, and that problem is that in the case of this current carrying conductor, the current is not really a vector. The current is a scalar quantity. It is the rate of change of charge that flowing through the conductor. So therefore, one cannot use the current as a vector, right? What is the vector is you could consider a vector which is in the same direction as this current carrying conductor and has the same length as the current carrying conductor. Now, in such a case, however, we can say that such a vector can be written by L, right? Of course, you would have to put an over bar about this because this is a vector. So I'll just write, actually this should be small l, because L is inductance. And this can be said to be a vector in the direction of the conductor, right? So, and this vector or rather this vector L, has two parts. One, it has direction, because the direction is in the same direction as the current carrying conductor, and it has a length. So the length will be the length of this current carrying conductor. Now it is also important to note that this magnetic field will be acting throughout the length of the current carrying conductor, right? So this current carrying conductor, which is placed in this external magnetic field, is acted upon throughout the current carrying conductor. A force will be produced because this magnetic field is acting throughout the current carrying conductor, right? So therefore, the force produced is not just proportional to the flux density and the current, but also the length of the current carrying conductor, right? The longer the current carrying conductor, the greater the force will be produced. The shorter the current carrying conductor, the lesser the force will be produced, right? So if we come back here, we have to write this last quantity, which is BIL sine theta. Now it's not very clear. Let me give another notation. Let me say, what else can we say for length? Let me say W. Actually, W is more like width. Yeah, W is okay, I guess. What else can I think of? Yeah, I think W should be okay. So let me say W is the vector in the direction of the conductor. Typically, it is always written as L. The reason why I'm writing it as W is just because you can't make out any difference between I and the length. So this is the equation for the magnetic force. That is, it is the flux density multiplied by the current multiplied by the length of the current carrying conductor and the sine of the angle between the flux density and the current carrying conductor. So this is the magnetic force which is produced. So this magnetic force can be said to be produced on this conductor depending on the length of the current carrying conductor, the strength of the current, and the strength of the magnetic field, and of course the angle between the magnetic field and the current carrying conductor. Now of course, let's go back here and do a little bit of analysis that the same can be said here as well. Of course, this is a cross-sectional area, so let's go back to our browser and let's look at a diagram of a single-phase induction motor. So let's take a look at this. Now, this is the rotor, which basically is, since it's a squirrel cage induction motor, it consists of a bunch of rotor bars that are short-circuited on both ends. There is a stator. Now, this stator here contains all the windings. So, when a current flows through the stator, it will produce a magnetic field in this air gap, right? And that magnetic field is going to induce a current in the rotor, due to which current will flow in the rotor bars. Now, the result is there is a magnetic field which is acting on this rotor, right? On each rotor bar rather. So therefore, we can apply this same equation to each and every rotor bar. So each and every rotor bar is experiencing a mechanical force which is proportional to the flux density, the length of this rotor bar, the current flowing through the rotor, and the angle between the flux density and the rotor bar. So this equation can be applied to every rotor bar in the squirrel cage induction motor, due to which we can therefore calculate the force on the rotor completely itself, right? So we can find out, using these equations, what is the force that is being experienced by this rotor. And therefore, once you notice the force, because as we go back, let's go back here. Once you know the force which is being acting on the two rotor bars, right? And if we know the force acting on all of them, we will know that there is a torque which is produced on this induction motor which will cause it to rotate, right? Now, before we continue, I'll talk a little about I'll end this lecture now because it's already pretty long. In the next lecture, I'll talk about some of the other impacts of this. For example, what will be the angle between the magnetic field and the current carrying conductor. For now, we have a sine theta. But in the next lecture, we will see that in the general case of an induction motor and most motors, due to the construction, this theta is close to 90 degrees in vast number of cases. Therefore, due to the construction, you will see that this construction of an induction motor, due to its special nature, will always ensure that the flux density is orthogonal to the current carrying conductors. So, with this, I will end this lecture. The main purpose of this lecture was to describe this equation, right? This equation of the mechanical force which is produced on the rotor bars, or for that matter any current carrying conductor that is placed in an external magnetic field, right? And the reasons for this, have we already seen, are vast. We've seen that because of the magnetic field, an EMF is induced in the conductor, and the conductor itself produces its own magnetic field, and this magnetic field interacts with the external magnetic field to produce a mechanical force. So we've gone through this entire deductive process, and now we are trying to use this equation, and this equation is due to the result that we can use the cross product to determine the mechanical force, because this cross product is between two vectors and the result is perpendicular to the plane formed by these two vectors, which is exactly the case of a mechanical force being produced by a magnetic field interacting with a current carrying conductor, right? So with all this, I will end this lecture. In the next lecture, we'll talk about certain special cases of the induction motor, and then I'll tell you about why, even though this is a very good way to determine how an induction motor works, this equation really is not much use in determining the magnetic or the mathematical model with which we can simulate the induction motor. To simulate the induction motor, we use another approach to determine the electrical torque. But still, this discussion is extremely useful in determining how an induction motor works and how to actually determine some basic mathematical equations to determine how the mechanical force is produced so that the induction motor eventually rotates. So, if you have any doubts, please do post either in the comments or message me on social media or send me an email, whichever is your preference. Otherwise, I will see you next week where we will continue with this topic, and rather the special cases that I spoke about here. Thank you so much for listening, and goodbye for now.